Uh, is this working now? Is this working now? I hope it doesn't lag or cause any issues. Hey guys. So I haven't changed Wi-Fi, but then the fuck. Sai, take what Sai. Try to read the problems. Okay, try to read the problems. Let's try to read this problem and then let's try to read this problem. Okay. It's an interactive game. So probably a good problem. Let's try to read these two problems. Okay. Can you guys hear? The fuck can I do now? Why? See, internet speed we can see somehow being fine. And if you see here, what are all using internet? I can show that I think. Is this not enough for streaming? Okay, let's try to read these two problems. Okay, first let's read this and then let's read this and then let's try both. There are n octopuses on a single file trail on Inas Mountain, numbered from 1 to n. I'll try to keep this to know if it got disconnected. If it gets disconnected, uh, yeah. There are guys. Try to read the problem. Take pen and paper and give your best. Okay. There are n octopuses single file trail on Inas Mountain, numbered from 1 to up to 7, and the octopuses has certain initial health value AI. Okay, where AI is in between these two. I remember this problem. In contest, I haven't solved itself. I only did one problem, yeah, and then I left. Like problems that I have tried already. Plus consecutive octopuses with indices L up to so on, L plus 1 up to so on are. Each boulder crushes consecutive octopuses with indices. Let's try again. I mean, I have read this problem once, but let's try again. You can choose the numbers L and R arbitrarily for each boulder. Okay. So a boulder crushes consecutive octopuses, it seems. For each boulder, the health value of each octopus, the boulder crushes is reduced by 1. However, as octopuses are immortal, once they reach health 0, they will immediately regenerate to a health value of k. Find the minimum number of boulders that need to be thrown to make the health of all octopuses equal to k. Okay, so as any normal problem, let's try to make some observations and then try to say what would be the minimum way. I mean, it's a good problem only. Even though I messed up in contest, I remember that I messed up this in contest, but it's a good problem. So let's try to read it. In one operation, we can do minus 1 to minus 1 to some range, it seems, and we should make all of them as reminder 0. That's the problem. So problem seems good, right? We have some array values, and then this is what you can do, and then it's, is it impossible at sometimes? No, right? Because you can always choose l comma r equals to 1, keep reducing it, so you can always make it as zeros. So you guys have read the problem. Did you guys understood the problem? Yeah, they would have said that. Lagging. So let's try the problem, guys. We have an array 1 to 1 less than or equals to a less than or equals to k, can choose L to R and reduce it by 1. Minimum number of moves to make it all k. So this is what we need. Okay. So this is what we need, right? Is the problem clear? So whatever the problem is, we finally prove that this is the minimum. Prove that whatever the code we write, whatever the process we do is minimum. So we will show lower bounds too. We'll show a lower bound. So we can try to find lower bounds on array A. Given an array A, you can try to find lower bounds. Maybe before that, you can try to say some observations. Okay. In one operation, what can we do? You reduce L to R by 1. If we see differences array, is this a bit simplified? Maybe. So if you see not differences array, because yeah, differences array, because why differences array? If you do plus minus 1 to all these things, then it's like maybe not, maybe it's not useful, but let's try to see. uh, the difference between this and this is 1, but the difference between this and this is 0, the difference between this and this is 0, the difference between this and this is 0, and then the difference between this and this is minus 1, right? So maybe instead of looking at these many things changing, here only two things are changing, right? Sorry, this is minus 1, right? Yeah. So maybe let's look at this problem instead of that. So why here more things are changing, right? So let's look operation in this thing, and still the problem is not changed because there is a bijection, right? So the problem is not changed. Problem is not changed in the sense, I mean, you can totally think this is the problem. Problem is to subtract -1 from something and add minus plus 1 to the next thing. Problem, this can be the operation, and then you have an array. Okay, array b of I, let's say b of 0 equals to a of 0, bi equals to ai minus 1, I greater than 0. Why am I just trying to see this? Because just because here two things are changing after an operation, here more things are changing after an operation. That's the only reason. Okay, see, we should try for some lower bounds. We should try for lower bounds. Okay, because we should try for lower bounds. So we are doing -1 here and then +1 here, right? So yeah, b0 must be applied some -1s, b0 -1s, right? b0 must be applied that many -1s. What happens when we do? What happens when we do the first thing as -1? When we apply, so then it is just -1, right? I mean, what happens when you do everything as -1? Then this will get -1, everything else with 0. That's it, right? So we have two types of operations. One is -1, 0, 0, 0, 1, 0, 0, such things, where L is this, okay? And R is this, R plus 1 is this. Or when we choose everything, we have this 0, 0, -1, 0, 0, 0, all are zeros. I'm just telling, these are the only two operations. Like, you can either choose, sometimes the +1 will go out of the array and it will not be there. So an operation could have been like this or like this, right? These are the only two operations. Till here, is it clear a bit? Uh, just because lesser things are changing here, right? Because here more things are changing. Here O of n things are changing. Here only two things are changing. That's the only reason I'm trying to convert the operations from that to this. So what does this say? An operation is you can do -1 and then do +1 later, or you can do -1 and you need not do +1 later. This is the operation. This is the operation clearly in this array of n elements. Okay. So if we look at BC, so we must, so now I'm again writing the same thing. See, why am I trying to find must be applied things? Because we should try to find lower bounds. Because you have to prove that you must do these many operations. So given a problem, it's not that you don't know what to do. If you know proofs are simple, you know what to do. Like, okay, at least these many operations should be applied, right? At least these many operations should be applied. And then but then you can also make things as 0 by doing plus 1, right? So let's try to keep it simple. Okay, finally all a's become 0, right? So they must have been added, bi's become 0. They must have been added minus bi through operations, right? So finally, like the result of their operations, some plus one, some minus ones combined, it should have been minus bi. Okay. Finally, you should do minus bi to everything in here. So the result should be minus bi. But there is reminders too, right? Okay. Let's just think for a minute or two. So minus bi in the sense, in terms of both plus 1 and minus 1, if you find a reminder k, that should be minus bi is what I am trying to say. Okay. All plus ones and minus ones. Okay. So you have to make it minus, right? You have to add minus bi to that. To add minus bi, maybe you can add this total sum should be minus bi finally. So what can we say? We can either do minus ones or we can do minus one and plus one. So we can only make them positive using this thing. This is very simple, right? This is just minus one. This is just minus one. This is minus one and plus one. So what does this mean? And then you have to finally make everything as minus bi, and that should be the minimum. I've tried this problem in the past, but still, let's see we can solve it or not. So finally everything should become minus bi. Anyone has anything? So some minus ones are coming, plus ones are coming. Let's try to see. Plus one is coming only here, right? If this is the only thing we can do, then I mean these are just some total considering operations, right? But some doesn't change with this type of operations. Some doesn't change. See, mm, here some doesn't change. With these operations, I'm again trying to see prefix sums, but then that's useless. Reminder, mod k. I mean everything is mod k. Okay, which finally it's very fixed that we should get minus bi mod k. Okay, finally it's very clear that we should get minus bi mod k. So let's just say for each I, let's say we got p of I plus ones in operations and m of I minus ones. Okay, this should be this much. I mean, I don't know why am I writing complicating this, but See, if I have not solved a problem, it takes somehow difficult. It's somehow difficult for me to solve the problem again. Okay, let's say this is the value. Could we have, so for every plus one you do a minus one here before that, and you can do some minus ones too. And you have to make all these things zero. Or if you add an element here, that could have been anything, and then you can consider this plus one as adding plus one to this. This doesn't matter. We have to make all these things as zero. So let's try to see. You have to make all these things as zero. If you look at this thing, we can either make it plus ones or we can make it minus one, right? But if you are making it minus one, we are using these things just minus ones here. Or if you are making it plus one, we will be restricted to, we must apply minus ones on here, right? So every time you make plus ones, that says okay, you must apply these many minus ones here. So let's look at this thing. Okay, let's say it is like 1 or 2 k minus 1. K minus 1 can be made 0 by using k minus 1 minus 1s or 1 plus 1, right? But then what happens? But then what happens? The fuck? I'm struggling because I have already solved this problem and then I was not able to solve before. Let's try, guys. Maybe we can solve this. I need water too. We can say one thing, right? We must apply these type of operations of total sum at least. We can say that at least. And what can we say with this operation? With this operation, you can decrease one, but then you will increase the next one. So with this operation, sum doesn't change, but then some things can decrease and then some things can increase. So if you see the last element, we can either decrease it using these many things or increase it. Is it beneficial to do both increase and decrease on this last element? If you look at last element, we can either do these many minus ones to make it zero, or we can do plus ones. But then if you do plus ones, So these operations have the restriction, right? Plus ones have the restriction. If you are doing plus ones, it's necessary that you apply minus ones here. That's the only restriction, right? Minus ones you can do a bit more freely. So to increase things is being a bit bad. So to make things increase things is being a bit bad, right? Let's just assume that you either increase something or you decrease something. Why not do both? Let's say let's I mean, why doing both is bad? If you are, like, what I mean is either one of this is zero is what I'm telling. If you are both increasing it and decreasing it at some point, so you have your plus one here, you're decreasing it, and then you have that one here, right? Because if you are increasing it, there is definitely minus one here, and then you are decreasing it, right? Instead of this, if you are decreasing it like this, instead of these two, you could have just done minus one and then zero, do nothing, right? Instead of, let's say, for some index, you are both increasing it and decreasing it. Let's just say this thing, okay? You're both, I mean, I'm just trying to see, we are increasing some things, we are decreasing some things, right? Let's say these things, this is also total positives applied on some index minus total negatives applied on that some index. This should be this. So I'm just seeing if both of these can exist or not. If you try to see that, let's say something got plus one and something got minus one, both. If this one got plus one, definitely it had minus one. This would have been operation. If this got minus one, this would have been plus one. Because I can assume that there is this z and it can always be anything. So all the minus ones can be thought as like plus one on this. Okay. If you are ignoring the n plus one element, and the final condition is all should become zero, n plus one can be anything. If this is the final condition, then minus one and plus one, if something is being applied on both of these things, okay, what can we do? Instead of that, we could have just done this. So this simplifies the problem that finally you decrease some things, you increase some things, but you don't do both on some index. This is a good point for us. Maybe now it's very clear, right? Now some things are decreasing, some things are increasing. So some things are coming down to, I mean, this is the simplest thing anyone would have done in this. Okay, in this array, I mean, I did unnecessary things to come here, but then now in this array, we can see that some things will only get decreased or some things will only get increased. It's useless to apply both increase and decrease in different operations on something. This is clear, right? This is a improvement. See, just observing that either p of I 0 or m of I is 0, just observing this is not that difficult, right? But this seems, now this simplifies a lot, this simplifies the problem a lot, right? What does this say in the original array? If you see in the original array, what does it say? It says decreasing all these things and then decreasing these things is worse than decreasing them together. That's what it says in the original array, but somehow still let's look at this thing itself. Okay, we have minus ones, we have plus ones. Some things will totally get decreased, some things will totally get increased. So it's like some things go down, some things go up. Okay, some things go down, some things go up. Now, now we know some things are going down, some things are going up, but then we have to make them as zero, right? So now we want more number of minus ones on this side. We want more number of minus ones, right? We want more number of minus ones on this side so that some things go down, some things go up. Do we still have viewers? I know. I should trim. I will trim in some days, but yeah. So they will either decrease or increase. This simplifies the problem a lot. Values will either decrease entirely or increase entirely. Okay, this simplifies the problem a lot, right? But then we have a restriction. If things are increasing, we need more decreases in the before. That's the restriction we have. So if you look at this thing, so let's try to see from the beginning. Let's say we have something till I. Let's say we found something till I. To make all till I 0, and when you make all of them as 0, till I, if you make everything as 0, by reducing some things, by increasing some things, first element you can only reduce it, we know that. But then the answer would be number of ones. Okay, number of operations applied itself. The answer would be number of operations applied itself. You have to make the sum of these things 0. Okay. So when you are at, let's try to use this itself, that either increase or decrease. At I, you make either decrease it or increase it. Suppose if you are increasing it entirely, okay, problems won't be this difficult because this is a problem that I have not solved already. I'm taking more. My every stream is a failure somehow. Some problems will get solved instantly because yesterday also I solved a problem day before yesterday or yesterday. Suppose if you are increasing it, can I just claim something? Can I just claim that answer equals to like minimum of b of I comma k minus b of I or such thing? You either increase it or decrease it, right? But then this cannot be true because you cannot use more increases. So number of minus ones applied is also number of operations, right? Number of minus ones applied is also number of operations. So if you look at first element, you cannot apply plus ones on that, right? You can only apply minus ones. So if you see first element, b of 0 must be applied negative. So we know what gets applied there. So we do b of 0 minus ones. Okay, we do these many minus ones, and then from 1, from index 1, we can do b of 0 plus ones too, because we have already done that much, that many minus ones, we can do that many plus ones too. Okay, so there is like this trade-off. So you choose something to this, you choose something for that, but then there is a trade-off that you cannot increase things without decreasing before, right? That's the only trade-off. Now again, b of 1 can either be increased totally or decreased totally. But if we decrease, we get to add. If we decrease, it allows next things to increase, right? So we have this thing. B of 1 can either decrease or increase, but what is the advantage of this whole thing? What's the advantage of this whole? What's the advantage of this whole thing? You either, whenever you decrease b of 1, you have the advantage that you can increase the next things, right? So so for a prefix, if I maintain something like, okay, something like minimum number of operations to make this prefix all zero while applying z minus ones. Without plus ones. So What I mean is, so if you see this structure, doing minus ones is good, right? But then plus ones will consume those minus ones again whenever we do plus ones. So what do we need here is, see, we are trying to brute force everything now. We found this point that anything will either decrease or increase. We are trying to just use that point. We are not trying to get more things from the problem. We're trying to just use that one fact and then somehow brute force everything. I want to cover all the possibilities of this being reduced and this being increased. But then it seems like, okay, 2 power n possibilities, right? But then what all matters is, when you do minus 1 plus 1 together, minus 1 plus 1 together, some minus 1s are individual minus 1s. Number of individual minus 1s is the only thing that matters finally, right? For the next index, what matters is, okay, some plus 1 minus 1s, some minus 1s have been happened. What matters to the next index is number of minus 1s. It doesn't matter how many have been decreased, how many have been increased. So we're trying to brute force everything. That's one simple solution we can think of, right? Just we got this fact that either something will be totally decreased or totally increased. We are trying to use that and then somehow brute force this. Okay, so minimum number of operations while making. So what I mean is, some operations plus one minus one plus one already has been compensated, right? But then non-compensated minus ones, how many do we have? If we maintain this as dp of uh, k plus 1, okay, dp of k plus 1, where dp of x, if x less than 0 means, sorry, if x less than or equals to k means you can apply x minus ones have been applied without plus ones. Okay, so do you guys get what I'm trying to say here, what I'm trying to store here? Okay, because see, we have so many possibilities. What all possibilities? If x equals to k plus 1, then let's say with number of minus ones greater than or equals to k plus 1. I'm not maintaining for k plus 2, k plus 3 and so on, because maybe this is enough to proceed further. Maybe I can group them all together into one k plus 1. Okay, so in dp things may look complex, but what we are trying to do, we're trying to brute force all decrease and increasing things. I will try to make things clear for you people. So we are trying to see, we got one simple fact that things will either decrease or increase. Now we are trying to use that to brute force everything. Okay, now we are trying to just use that to brute force everything. Okay, see, we have a restriction. So number of operations is number of operations is number of minus ones. Right, but we have some restriction on applying plus ones. To apply plus 1, you should have applied minus 1 in the prefix. This is the restriction. So we're trying to brute force. For a simple proof, we're trying to brute force all possibilities. But among them, only some are allowed, right? Only some are allowed, because you cannot increase b of 0 by plus 1, right? Only some are allowed. So whenever we do dp, we group things. Dp is about seeing bijection something. Let me go and get some water, I'm trying to shout. I got water. So the problem is being simple, right? I hope I have viewers. Yeah, the problem is being simple, right? We have minus 1. See, so dp is, we know that some things will be reduced, some things will be increased. So we are trying to brute force this whole structure. Okay, some things has been reduced, some things has been improved and all. But then while brute forcing this whole structure, what happens? While brute forcing this whole thing, what happens? You cannot, you cannot reduce this if if the sum of increases and decreases so far, the sum of increases and decreases so far, sorry, the restriction is you cannot increase this, you cannot increase this if the only restriction is, see, so now we either do, see, idea is we brute force this shit. It's a 2400 problem, but the stupid idea is to brute force everything. Find just this fact that you either decrease or increase and then brute force everything. That's the idea, because we can brute force now. Why? We have one restriction. What's that restriction? That restriction is you cannot increase this much. But how much can you increase? That depends on the resulting negative sum you have done here. The resulting negative sum you have done here. So if you have with negative sum 0, what's the minimum answer? With negative sum minus 1, what's the minimum answer? Means number of greens minus number of reds, everything. With negative sum minus k, what's the number of answers? I think with negative sum minus k plus 1, k plus 2, you can combine all these things into one. What's the answer? Like among all these things being the negative sum, what's the answer? If you have all these things, you can again brute force this being positive, this being negative, and then find these things again easily, probably. So the idea, if you believe that proofs are simple, what can be a simple proof for this thing? Maybe brute force everything. Brute forcing everything can be a simple proof, right? So do you guys get this problem a little bit? So while brute forcing, we have 2 power I possibilities, 2 power I possibilities. But then what dp means is we don't care if there are 2 power I possibilities. What all we care is what is the resulting positives minus negatives sum. That sum is the only thing that restricts this being positive, right? So we are grouping them into positive minus negative sum being, it can never be positive because the resulting sum cannot be positive. That cannot happen. So or else we should have considered this too. Do you guys get what I mean? Please try to understand, because If you guys complain I'm going slow, that's time for you to think, that's time for you to get familiar with the problem. Okay, so some cannot be positive anytime. So there are 2 power n things, but then we're grouping them. DP is always about you group. There are so many things, but then you group them, and then you can extend the groups again. You can find the groups again for I plus one. You don't touch everything. You group things, and then you make bigger. You make newer groups. Do you guys get what I mean? So, among all possible allowed things still here, you have minimum number of operations that add up to zero, minimum number of operations that add up to minus one, minimum number of operations that add up to minus k up to so on, minimum number of operations that add up to greater than minus k plus one. Let's say you have all these things. Okay, now, how do you find all these things? You have two things. You either do total positive or you either do total negative. So, with these two brute forces, you should be able to find again all these things, right? So, if you are doing positive plus, if you are doing negative, then all of these are allowed as it is. But then all of them will be shifted somehow down, right, by this value. That's it, right? All of them will be shifted down by that value. Okay. But if you are doing this value, if you are doing this value, all of this you cannot use. Okay, because if it is minus 1 and if you should do plus 2, you cannot use those things. You can only use these things, all of these things, to get there. So how can we do these things? Like, try to take this range and then move that little bit. So, but the problem is mostly doing this only, because otherwise we cannot find more nicer things in this, I guess, right? Because we have to brute force. If you are not brute forcing all these possibilities, we have to find some other great fact. I don't think there exists something like that. This seems the most appropriate thing, because okay, the sums are just from 0 to k, right? So probably this is the problem. Is k a very big number? I hope k is not 1 in 9. Okay, what to do if k is 1 in 9? Maybe we can just brute force. Maybe we can find the answer easily. Maybe we can find the answer in a better way. Okay, let's try to see that. So, few things, for few things, doing negative would be beneficial, right? Doing negative would take lesser operations. For few things. For few things, doing positive would take lesser operations, right? What's the cost of going from negative to positive? What's the cost? See, k equals to 1 in 9. Maybe not brute force then. Maybe we want brute force. Maybe there is a greedy way. Maybe there is a greedy way. Let's try for that, okay? Maybe there is a greedy way because the things are not too complex, right? Maybe there is a greedy way. So what's the, because either green or red, right? So you can either do the green or red, and you know the cost of going from here to here too. If you go from here to here, what's the cost? because it's simple. Looking at this array itself is the best. They either increase or decrease, but then we want, see, this is still a big thing because now we know they either increase or decrease. With either increasing or decreasing, we should find a greedy way. So few things, let's try to apply more things. Okay, this is DP idea. Sometimes it can be done. Sometimes it is enough. Sometimes it is not enough. Okay, sometimes this is enough. Sometimes it's not. So here as k is 1e9, we have few things with, so so for everything where m of I is less than or equals to p of I, we do negative. This is for sure we can say, because if negative is lesser operations, doing positive is useless, right? All these things are negative. Now, 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 let's say everything else is positive. For now, let's say everything else is positive. Let's try to write some more things. Okay, let's say all these things are negative and then everything else is positive. Then, if you make that negative, what happens? We get minus k things, right? So everything else positive. If this is allowed, then we are done. So now we are trying for something greedy. Okay, because we are trying for something greedy. If see, if negative is better, we are keeping them as negative. This is always good because negative itself is minimum. So keep them as negative. This is true. So now we are worrying about positive being minimum things, right? So positive like k minus 1, k minus 2, these things. Positive being minimum. This we are worrying about. Okay? These things you are worrying about. And for these things, let's say they are currently x up to so on. Let me check my message. So if this was x, what I mean is by greedily, if this is allowed in the sense some positives are not allowed, right? You cannot keep more positives here. So now we are trying to make it allowed by, So we either do k or we do k minus x, right? So we are doing x positives, but instead we would have done k minus x negatives, but then 1 minute. Positives are not counted anyway, right? Positives are not counted. So the making things negative is good. So converting this x to this would have costed k minus x to the cost, but it will totally help in things to stay positive. So let's say few are negative, okay, and then somehow this cannot be positive. With the negative we have gotten so far, somehow this cannot be positive. Then we will make it negative. Would this greedy be enough? Would this be enough? We have to think. So, what should we have to think? I think that is too bad greedy. I don't think it may work. But what I mean is, we have some red things are positive. Let's say we have some positives, we have some negatives, right? What I'm saying is, negatives are all fixed already. From the beginning, some positives are not allowed. If this positive is not allowed, we'll flip that, okay? And then we keep going. But here we have a positive. Now we have some other allowed positives here too. Instead of flipping this, would flipping this be better? Might be, right? Because flipping that would have only added this much. But then here it is 0. Flipping that would have only added that much. But it might have allowed this to stay positive, right? So whenever we are trying to flip this thing, we can try our best to save this, okay, we can try our best to save this and flip something smaller. In the previously there things, instead of flipping this we can just flip something smaller, that is before, right? Instead of flipping this we can flip something smaller, that is before. So what does this say? No, but flipping this might not have helped with this. If it can help, then flipping that would be better, right? Let's try to see it some more time. Let's try to think for some more time. I mean, this again brings down to maintaining everything, but then I don't think we can maintain everything, right? It's looking like we have to maintain everything. Like if you're brute forcing, if there is no greedy, but then let's try to see some more time. Flipping this will increase allowed range a bit, right? It will increase allowed range a bit. These green things are all just the help they will do. You have that much of help. That's it. They're just in middle. They will help a bit. But after the help, what's the optimal arrangement of the red things? What should go down? What should stay up? Is the question. Let's say if it has gone above, let's say if it has gone down and then it helped everything else. Is that fine? Is that good? Let's say it has gone down, but then it has helped almost all the positives after it. Uh, I just died in your arms tonight. Must have been something you said. I don't know how you guys are staying and looking at what I'm telling, but so we have these green things helping. We can turn some things green, but then that costs us some operations. Turning this will cost this much, but then it can help the remaining things. So this is the structure of the problem. Turning this may help, but then it will affect. It seems brute force, but then these in between negatives don't help at all. They just say this much relaxation you have. That's it. That's all they do because they try to help in between. That's it. So we have these positives. Flipping them will cost you this much, but it can help the other things to stay positive. So what does this say? Some till here was not enough to keep this positive. So some till there would have been, because this is a smaller thing, right? This is a smaller thing, less than k by 2. So the sum till here has become less than k by 2. And then that's not enough to keep this up. So we are reducing it like this. So this would have been greater than k by 2. So this seems very tight, right? So what is a lower bound? What's a lower bound? I think instead of thinking, I should have just gone for lower bounds because some other people can solve the problem quicker, right? Quicker than me. So if you look at this, what is a lower bound? Plus 1 comma minus 1 doesn't change the sum, right? So maybe take prefix sum. So I think greedy would work here, but let's see. Take prefix sum, let it be yes, okay. Let the prefix sum be yes. What does this say? Sorry. I was trying to see if the plus if this S is there, would that sum That's some. We have to do something greedy on this. So let's try some more time. So I think if it becomes tight or something, so if you see something being tight, okay, if if the prefix sum of these things, even when everything is turned down, I think we should be able to say something greedy on here. If you have done this thing, trying some greedy also would work. Don't judge easily, guys. I may do some other kind of problems easier because this is an unsolved problem for me. Previously unsolved. Either reduce it or keep it same, and then you want. So what does it say when it fails in some greedy way? Fails means like it's becoming somehow tight, right? Like, okay, you cannot keep it red. What does that mean? Like, if you cannot keep it red means like the whole sum till here is, if there is, instead of turning this thing, if there is something smaller, turning, if there is something bigger, turning that, turning that, if something is bigger, turning that would have reduced lesser cost, would have increased lesser cost, because bigger things will have smaller green, right? If something is bigger, it will have smaller green. Okay, so maybe changing something here would have increased little bit of green and then might have allowed it to stay. That is true. Instead of turning this, what is better? Instead of turning this, if this is maximum, then turning that would have been better. Why? Turning anything here would increase it more, right? But if it is a small thing, turning it will increase it a lot. But instead of that, you can turn something else that increase smaller, but then tries contributes helping also. It contributes helping too. So you always have few things. We need some greedy algorithm probably, but how can, I mean, greedy ideas can be just like, okay, everything is, all red things are red, maybe trying to make few things green now, or everything is green, try to make best things as red. If you have turned it green, instead of doing that, turning this green will increase the green sum by this much. If this is x, turning this green will increase the green sum by k minus x. But then, instead of turning this green, if you could have turned some some bigger reds as green, you would have gotten, you would have only increased this much, right? But that would have been enough to cover this thing. Some problems I solve instantly, some problems I cannot. Should I read the next one too? If you guys don't believe me, I can solve higher rated problems. I can show it here. In 2023, I used to solve 3000, 29, 23, 28, 28, 28, 35, or more problems. But then getting stuck on this, don't judge me by this one. Let me read this also then. Okay. Consider the following game for two players. You guys read that. You guys also can try to read that. Okay. We can come back. Or see, this is a problem which I got stuck in the contest itself. Like that contest itself. Cannot probably solve it. But then if we use our same ideas, it should be solvable, right? Like greedy may work. There can be some lower bounds. I'm not able. I have not tried to guess any good lower bounds, right? What are some good lower bounds? Like you cannot. What are some good lower bounds that say even if you make everything negative, let's say that's not enough to keep it positive, then that's like a lower bound. This must be reduced. So let me read this too. Okay. Consider the following game of two players. Initially, an array of length n is written on blackboard. Game consists of rounds. On each round, the following happens. Initially, n numbers are written. Game has rounds. The first player selects any I such that I greater than 0, such that if there is no such I, the first player loses the game. Okay. The second player selects any j not equals to I such that aj greater than or equals to 0. Let d equals to minimum of ai aj, the values ij are simultaneously decreased by d, and the next round starts. So we have this n values. See here, probably some greedy works. I'm not able to just guess it. I mean, guessing should be easy, right? See, if there is a greedy, we can say such things like, okay, if this becomes negative, can you maybe can we say something about the first positive or last positive? Is keeping this like this always good? Let me read this too. It can be shown that the game always ends after finite number of rounds. Okay. Okay. So this is a good game, it seems. So we are given an array, and then we should find who will win and how they will win, and then we have to select the player and then win the game. So it's always possible that we can select the player and then win the game. So this seems a nice problem, right? So first player chooses something, second player games. I think we can work on this problem easily. So problems like this are rare because I've solved so many problems. Don't take anything from that. Let's try to see this problem. We can say a few things, right? Let's try to say what we can say. If only one, let's only look at non-zero elements. Let's if only one non-zero element, then first player wins, right? And then what happens? One will become zero, other will be subtracted. Okay, let's try to make some observations. Whatever we make, this we can say. If there are two things, then whatever he select, we have to select the other thing. right? If all zeros, second player wins. I cannot be zero initially. Okay. If only two non-zero, then whatever the first player takes, whatever the second player takes, for the next round we will have only one thing. Okay. If a1 equals to a2, then first player wins, second player wins, right? Because after this what happens, both will become zero. After this both will become zero, else first player wins. Why? After this one will stay. I remember my friend solving this very quickly in contest. Not my friend Tyrob is solving that very quickly in contest. The previous one. They are not increasing my rating. I've asked this guy. Damn, I'm getting requests. I really need your help regarding my online assignment. The fuck? Mm, first player wins. Right. Because after this, whatever they choose, after this, what happens? So now this is the case if there are three elements. So now, if there are four or three elements, okay, if there are three elements, after you take this, so who has more freedom? First player has more freedom, right? Of winning, like here. So can first player do something so that he can win again? So when there are three things, a1 equals to a2, only then second player will win. So first player has a bit more freedom, right? So so let's see them in increasing order. If uh, a2 less than a3, then first player can choose a2, okay? First player will choose a2, and a1 is less than or equals to, right? If first player chooses a2, if second player chooses a1, then one of them will become zero, right? One of them will become zero, and then things will be unequal. So first player will win, okay? If 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 second player chooses a1, p1 wins. Why? Among a1 and a2, now things will become unequal after this. One will become zero, other things will become unequal. If second player chooses a3, then again p1 wins. Why? He has chosen a3, right? Now what will be, no, now we cannot say. 1 minute. Now we cannot say because, okay, sorry, because a1 could have been equals to, if a1 equals to a3 minus a2, we cannot say. So let's not look at this. Let's say he has picked a3. If he has picked a3 or a1, let's say he has picked a1. If you take this, we are again left with the same thing of a3 minus a3 equals to a1 plus a2 thing. Okay, a3 equals to a1 plus a2. We are left with that. A3 equals to A1 plus A2. So if we choose A1, A3, again we are whatever he chooses, we are left with. So always we are being left with what? Sorry. Always we are being left with A1 comma A3 minus A2 or A2 comma A3 minus A1. Only these things, only these are the things we will be left with, right? Whatever happens. It's like if you see them in increasing order, he chooses something, then what it becomes, this thing goes into there and subtracts that. Right, this thing goes there and subtracts that. So if A1 plus A2 equals to A3, then whatever the first player chooses, it becomes this equal. So second player wins. If A1 plus A2 equals to A3, then second player wins, P2 wins. Else, else you can just choose anything again. You can choose anything. And then what happens? It will become, okay, 1 minute. Yeah, you can choose anything. If you choose A2, whatever he chooses, if you choose this, if he tries his best and then choose A3, if he choose A1, he will definitely lose because then again it's non-equal and then first player will win. Even if he chooses best A3, then again he will lose us because A3 minus P2 wins. Sorry. So it's being the same again, see? A bit same. Till here it's just work, okay? It's just work. We are not even using any great logic. I can never use great logic. See how I stuck here, how I got stuck there. So now, if A1 plus A2 equals to A3, then we will win. Else we won't, right? So now again, let's see. Else P1 wins. P1 has very good chance of winning. P1 has very good chance of winning. P1 will only lose in some weird case, okay? So now, if there are three elements, okay? If there are four elements, okay, let's see. F4, can this be just this? Yeah, maybe, because still is the same, right? Because it came down to this thing. If A1 less than A1 plus A2 equals to A3, P2 will win whatever you do. Because he can always make things as A2 minus A3 minus A1, right? You choose A3, it will become A3 minus something. You choose A2, he will choose A3. A3 minus something, right? So again, let's say if A1 plus A2 plus A3 equals to A4, if you choose something other than A4, okay, he chooses A4. Now what it becomes? What will it become? A1 something missing equals to A1 A2 let's say A3 missing. If he chooses A4, it becomes A4 minus A2, and then because this is equal, P2 will win. If this happens, whatever you choose other than A4, he will win. If you choose A4, again he will win. Why? He chooses something here and then he will win. So does this continue? We have to see. Else, can you always win in this else case? Why? You choose this thing. Let's say you choose smallest one. Okay. You choose smallest one. Whatever he chooses, whatever he chooses, what happens? Whatever he chooses, what happens? Things will become. See, in the remaining case, what he should do? He should try to not make this equal. Right? He should try to somehow not make them become equal. So if this happens, whatever the first guy do, he will P2 will win. But here we have to see one more time. Okay. Can we choose something and then make things favor to us? Let's just choose A4 itself. Okay. If you choose A4, whatever he chooses, what it will become? What it will become? A1, A3, A4 minus A2. So now, because this can become smaller, and then it can happen that A3 equals to A1 plus A4 minus A2, right? This can become smaller. That's why I'm not choosing A4. Why? If something has been reduced and then again if it becomes A3 equals to A1 plus this thing becomes smaller. Then again P2 will win. So we have to just check it a bit careful here, okay? If this happens, P2 will surely win. And for what other cases can P2 win? If this happens, P2 will surely win. If that doesn't happen, does A1 has a way to always win? Does A1 has a way to win? We have to just see that carefully. Let's try to be a bit more careful. If that does not happen, what will happen? A1 plus A3 plus A1 plus A2 plus A3 less than A4 can be one case. A1 plus A2 plus A3 greater than or equals to A4 can be other case. In this case, we can choose A4 and win. How is the interaction work? Both will say their indices. Okay. Now we always know what are the elements. Well, we can choose A4 and win. Because even after choosing whatever he chooses, A4 minus A3 is again greater than the previous thing, so we win. If this happens, okay, is there a way where we can make things non-equal again? If this happens, and all these are positive, if we choose two things over here, what will happen? If he choose one thing here, and then he chooses A4, here If we choose a4 and if he chooses a3 and then their subtraction becomes less than a2, maybe then I hope we are correct till here at least, right? If every any other case, whatever you choose, this is what happens. After you choose a3, whatever he chooses, this is what happens. And if that doesn't happen, they won't be equal. So this is perfect. Here, let's just be careful and see if there is a way we can always win. P1 can always win. If that is true, maybe we are done. So the problem is maybe if a1 plus a2 equals to a1 plus a3 equals to a2 plus a4. Okay, then there is a problem. Let's say all are equal. Then you choose, then second player will win always. So that's there. What about here? Here, no. If all equal to, P1 can choose something, whatever P2 chooses, P1 can still win. Yeah, this is true. P2 wins. Even if all equal, P2 wins. That's why we are failing this a bit, okay? If all equal, P2 wins. Why? We take something, he takes something, gone. We take anything, he take anything, gone. That's just an extension of this. So if this happens, can we say if something like this happens, all will be equal because a2 greater than a1, a4 greater than or equals to a3, right? So let me think a bit, okay? Are those the only cases, or these two the only cases where P2 can win? What are all possible things here after you choose a4? So whatever you choose, maybe I'm complexing. Let's try to see some more time. I have work tomorrow. See, it can get too complex. We have to just verify here because we must do these things if n equals to 4, right? If n equals to 4 is given to us, we must do these things. So let's try to just look at it some more time because we must do these things at some times. It's all about just seeing this. Is there any other case where if this happens, if you choose a4, he can just choose a3 and then he will win. Why? Because a4 minus a3 plus a2 equals to a1. I mean, this cannot be happening. So here, if this happens, this is nothing but all are equal. So let's say us losing by choosing A4. We chose A4 and then we are losing. How would we lose if we choose A4? Let's say I chose A3. Then A1, A2, A4 minus A3 are left. And then it says probably if this is the bigger, because this is the if this is the biggest, then it's definitely not equal. That we have already evaluated. If A2 is the biggest, then A2 equals to A1 plus A4 minus A3, which is nothing but this. This implies all are equal. But let's say if we choose A2 instead of A3, A1, A2, A1, A3, A4 minus A2. If this is maximum, then again we are winning because that's not happening. But if this becomes maximum, then again that means A2, A3 plus A3 equals to A4 remaining things, which is A3 plus A2 equals to A1 plus A4. This doesn't mean all are equal. So is it like something's adding up to other things? Let's try to just look at that. Let's say if some things are adding up to other thing, then let's say then P2 will win. If this is our claim, whatever A1 chooses, whatever A1 chooses, A2 can choose other thing from this set, and then that will be removed from both, and then again you have a set where something is equals to something. So is it existence of S1 equals to S2 subsets or partition? So if these things exist, then P2 always wins. If those two exist, P2 will always win. Why? Whatever P1 has chosen from this subset, he will choose something else from that subset. And the sum is same. To let's say, then P2 will win always because same amount from both, either both becomes zero or both stays. So probably this is the answer, but let me try to prove it well. Okay, let me try to prove it well. If no subsets, no partition has equal size, if no partition has equal size, no partition splits equally. So this is why you guys should keep trying. Okay, this guess is not that difficult, right? This guess is not that difficult. And then if you guys can apply a little bit of math, maybe this works, is the thought I got. And then I thought, should I try to explore it or should I try to explain things? I thought, why not explore? Like, let's just try to look at that because that looks good. So this clearly gives out P2 will win whatever happens if this exists. If just this exists, if there exists some subset, this looks very tight. So this is probably the answer. So now, if no partition splits equally means we have to choose something, and then again no partition should split equally. Okay, we have to choose something, again no partition will split equally. So would whatever we choose, will it work? Whatever we choose, will it work? Because there is no partition at all. Okay? But then let's try to prove it inductively. There is no partition at all. But after one move, there can be partition or not, let's see. Then can after one move there be a partition? We're trying to use induction because inductively this seems correct for smaller things, right? At least for n equals to 2, it's correct. Partition exists, then partition doesn't exist, the other one wins. So, inductively, if there is no way to partition them such that their sum is equal, then after ai minus aj, can now there be a partition that that's of equal sum? This is the question. So let's say we now have s1 comma s2, non-empty partition of equal sum. Then what does that say? S1, let's say ai minus aj belongs to S1. Then that says ai in S1, comma, aj in S2 is a partition in the above set. So this is not possible. Whatever you choose, this is not possible because ai minus aj can never go into some partishable set, because if it goes once, see, we are using induction. After doing this, number of elements reduced by 1. Now we only have one ai minus aj. But if this becomes a partition, we could have had a partition here too. So now it doesn't matter. Whatever you choose, you can win. Whatever you choose. Whatever you choose, there won't be a partition at all. So guys, this is done. Do we have something? So what my claim is, if there is no subset, that's if there's no partition now that sums equal, after I move to, there will no partition that sums equal, because after I move, what happens? Something disappears. Because you would have a partition above too, right? So in this case, you can remove anything. You can remove anything and still you will win. If no partition exists such that the sum is like that, if sum is odd, such a thing will never exist. Okay, if sum is odd. If no partition exists, whatever you remove, it works. If sum is even, you have two partitions. Whenever he removes here, you remove there. Whenever, okay, he removes there, you remove here. Okay, that's it. That's the game. So we do brute force DP to find if there exists such a. So see how I solved the other problem very easily when compared to the previous problem. I will just do a DP to find all possible partitions. Okay. How to do a DP? Maybe I will maintain N cross and DP we can just do, right? N cross N also we can do because N is just 300. We want half sum, all possible subs. So let's say DP of N times hot husband. Haha. So guys, we tried solving this problem where we have elements, two people remove two elements, and then the sum will not reduce. So one observation. Yeah, bro, I could have taken flat, but I'm not taking somehow. It's a spacious one. It's spacious and expensive one too. Flat is cheaper, but somehow. Please try to help me, bro. Like try to say if you were following this problem or not, this interactive one or not. Like interactive one shit, right? Okay, it's you. So were you able to follow this interactive one? Like whenever there is a subset of two things being equal, we can solve the problem. Okay. Did you follow this problem, Pradeep KR? Say, bro, otherwise I'll say it again. So I just tried saying n equals to 1, n equals to 2, n equals to 3, but when I came to n equals to 4, it became more obvious. If a subset exists, whatever we do, the other guy can win. Okay. So now is that clear? If there is a partition S1 comma S2 with equal sum, P2 will always win. Is that clear? Like, because see, after seeing this, it's not that A4 equals to A1 plus A2 plus A3, but it is that even if this happens, he will win. Player 2 will win. So now I thought of saying existence of some such subsets as the S1 equals to existence. If a partition S1 comma S2 exists such that S1 sum of S1 equals to sum of S2, then he wins. P2 wins. And then I used induction to prove that else it will never exist. We can choose anything, but it won't exist. Else, in other case, you can choose whatever, but it won't exist at all. That I have proved by induction. Because if it has existed, what does that mean? Ai minus aj in this and this have equal sum. You can move this aj there. That means you had a sum subset in the top, which is not possible. By induction, you can remove anything, but still it won't be possible. But still it won't be possible. Do you get what I mean, Pradeep KR? See, whenever S1 equals to S2, we have this subset now. He takes here, you take from here. Because if this is non-zero, this also will be non-zero. He takes here, he takes here, and then sum again is same. And then again, if he takes here, you take here. So if there exists a subset, you are done. If there is no subset, I have proved that taking anything will work. So now I am trying to find if there exists a subset such that sum is same. For this, we will use DP to. Nice, bro. Kashimoto. So let's say let's say dp of sum dp of x equals to 0 if it's impossible, else it has some index with which it's possible. So some index like this, because I also want index. Let's say if it is possible, it will give me a highest index with which it's possible. Let's say we are maintaining this thing. Okay. Initially, d of 0 is initially what all is possible? dp of 0 is possible, not taking anything, right? Because at n equals to 2, that partition existing or not existing decides everything. So by induction we can say if that partition existed at one point, it will exist in the higher point too, because I'm trying to use induction. Let's say this belongs to this, and then the partition existed. That means ai here and aj here also the partition would have existed. So if no subset exists, taking anything works, and P1 will win. Because it's never possible. Wait a minute. Subset or subsequence are the same things, right? Okay. I will verify this once again. Okay. Whatever you remove, there won't be partitions, is my claim. Because whatever you remove, if there was a partition, here also there will be a partition. So whatever you remove, there won't be partition. So finally, what happens? When there are two things, whatever you remove will end up with something non-zero. That's it. Yeah, I'm just using DP. Hi, Donjay. I'll maintain two things, okay? So, so dp of 0 is possible. Okay, let's keep it there. So now from index I equals to 0 to I less than n I plus plus, let's keep it I equals to 1. So from these indices, we again have to maintain these things, right? So If we are not using a of I, whatever we have is right. If we are using a of I, if we are using a of I, max sum. So if we are using a of I, what should we do? If we are using a of I, what all subsets are possible? If dp of s minus a of I is true, then it's possible that dp of s will be 1 and dp in of s can be, and dp of s can be I. Why am I coming from bigger elements? Because I am trying to use dp of s minus smaller elements, right? So I'm trying to use previous smaller elements. So of previous iteration, before adding I, if this happens, before adding I, is it possible to get these things? For that reason, I'm coming from this direction. I could have maintained a temporary array. I could have maintained a temp, but then this is enough. So now, if I need sum too, right? So it's not possible at all. So now, how should we do the interaction? We'll go first. This end line cost a contest, and then we can just always do not done equals to 0. We can output anything. We can output anything. Okay. So we are playing first player. What do we do? While true. Okay. While true, we will find some index. We'll find some index that is non-zero. I'll just output that IDX. And then I will get a J. Right. This will just work because after this, what should we do? Yeah, this will just work. Each time an element becomes zero, complexity is not that high, and then it works. We will win. We'll get j equals to zero. Else, now we will form the subset. Okay. If it is odd, it's definitely not possible to make into two equal subsets, right? If it is even, then this makes good sense, and then we have that. So here, see out second, and then let's try to find that subset. Okay, let's try to find that subset. Let's try to find that subset. Let's try to find that subset. Okay, int required equals to sum by 2, right? While required, while required, s1 dot pushback of dp int of rec, right? And then rec minus equals to dp int. That's it. So what does this say, dp int? It just says with this index, it's possible to take that. So dp index, after removing that index element, we'll have rec again, and then it becomes zero. Okay. I'm trying to form those two subsets. Okay. So now our strategy is, if computer chooses something in S2, you choose something in S1. That's it. This is the strategy. Because two subsets existing, you choose something, he choose something. These subsets, one of them may become zero, still be equal. He chooses here, if this is non-zero, this will also be non-zero. So that keeps working. So now while true, okay, we need not even maintain this. While true, int j, scene j, computer chose j. If j equals to 0 or j equals to -1, break. Okay. Else, else, if, else, int idx equals to 0 for int I equals to 1, I less than n, I plus plus. If in s1 of I not equals to in s1 of j, I not equals to j is also handled by this. Okay. They both are not equal, and a of j greater than 0, then idx equals to j. I can do break here too. I need not do it, works. And then It is possible if you believe it, bro. We don't believe. Should I see if you're finding subsets correctly or not? Because here we have 10 plus 4. 10, 10, like this. Let's take these things. Here there is probably a subset. 10, what's the total? 10, 14, 20 is the total. 30 is the total. Right? Can we form 15? Can we form 15? Is 30 the total? Till here it's 25. 30 is the total. Can we form 15? 4, 10, 15. Yeah, we can form 15. So let's try to see if you are finding 15 or not. Okay. Why? Okay. What am I doing? I'm trying to the smallest end index possible. This be our thing, because what happened was 15 is possible with 2, 16 is also possible, 13 is also possible with 2. So now I will say dp index of x has smallest end index possible. Okay, that means what should we do? And dp of s equals to 0. So now what happens if this was already occurring, then we would not make it now. So now we are trying to make the tightest. That was not possible before. That's only possible with this index I. So these things are good. So now it will be 4 1. See, because I'm trying to find the smallest end index. Smallest end index is 4 comma 11, right? So that's why we got 11 comma 4. That's correct. Smallest end index where it is possible, because highest index claim is not correct, because I cannot use the same thing multiple times, right? So this would work. Do you get what I mean there? So now we are trying to find the smallest end index. Okay, smallest end index, because previously with too many things are possible, that's why it fucked up a bit. So now if you're doing all the steps correct, it's probably works. So let's just try to output it, submit it directly. So guy, why is it stuck there? Because if you think of a way where P2 will always win, that's a way you can maybe think of. Okay, if there is a subset, remove, they will always win. What did I do? Is it some small wrong answer? AI greater than 0, I have applied finding that. Oh, IDX equals to J. What the fuck was that? And how did it pass test 1? I should be very careful. Yeah, bro, I'm Telugu. Thanks, Tanjay. The problem is guessable a bit. And once you guess it, implementation is like trying to find a subset of some knapsack, famous easy problem, but then smallest n in X. It's not that difficult. Here, anything works is my induction proof. Here, take something in the other set. If they choose here, you choose here. If they choose here, you choose here. Because if this is non-empty, this will also be non-empty. Fast fingers. Mistakes, too many mistakes. They're not hiring me, bro. I haven't applied from 1 year, but recently I'm trying to apply. On experimenting on n equals to 4 leads there. But then, if you also give importance to the problem structure, then also that makes sense, right? If you give importance to the problem structure, because the problem is okay, one removes here, one removes here. That says, okay, if these two are equal, can we always have that and then we'll finally go there? So, problem structure, that's why we have to give the a bit of importance. Problem structure, seeing, we are seeing a1 plus a2, see, can can we generalize a1 plus a2 plus a3 equals to a4 and a1 plus a4 equals to a2 plus a3? Then you come to subsets easily. I don't know, bro. Think, add something, fake something, somehow write something in resume. That's it. Bye. Good night, everyone.